So in the section before, what we did is we found the zeros of our polynomials. Again, remember those are our x-intercepts or our roots. And what we did before is we were given one of the roots, and then we did synthetic division or long-form division to find the other roots in our more reduced polynomial. But what if I'm not given any roots at all? Well, let's look at the book. So we have this rational zero theorem, which is talking about the coefficient of the lead term and the constant in the end, and that relationship in between. But finding the possible rational zeros is basically summed up right here, where the factors of the constant term over the factors of the leading coefficient create all the possible combinations. So let's go into this and work this out. So if I'm looking at this, possible zeros, or the possible zeros for this, what they are all the factors of one number and the other. So we're looking at always looking at the lead coefficient and the constant. So all the factors of the constant term are going to be 3, so that's going to be positive and negative 1 times positive and negative 3. And remember, to get a negative 3, it's going to be positive 1 times negative 3, negative 1 times positive 3, and so forth. So then I'm looking at all the coefficients, the factors of the lead coefficient, which is 4. So it's positive negative 1, positive negative 2, positive negative 4. So all the factors, we're putting one over the other, so we've got all the factors of the constant on the top, positive negative 1, positive negative 3, and then all the factors of 4 on the bottom, which is positive negative 1, positive negative 2, and positive negative 4. So all the combinations, and I'm going to leave off the positive negatives for a second, is 1 over 1, 1 over 2, 1 over 4, then 3 over 1, then 3 over 2, and then 3 over 4. And then, of course, all the positive negative combinations of all of them. So these are all the possible roots of that particular polynomial. So for better or for worse, we're going to try out all the combinations to see if one sticks. So what I'm going to do first is I'm going to say, well, what if I try out the root of 1? So remember, if I try the root of 1, that means my binomial is going to be x minus 1, but we try out the root and do the synthetic division. And then what I have to do is remember that when we do synthetic division, we have to account for every coefficient of every degree. So this is the coefficient on x to the 5th. This is the coefficient of x to the 4th. There is no coefficient or term for x cubed or x squared, but then I have the coefficient of x and the coefficient of, or the constant at the end. So again, remembering the synthetic division, we go down, and then when we we go down, and then we multiply through. So 1 times 4 is 4. Then I add down. 1 times 16 is 16, and then I add down. 1 times 16 is 16, and then I add down. 1 times 16 is 16, and then I add down, so I have 15 now. So 1 times 15 is 15, and then I add down. So again, remember that this is going to be my remainder of 12. When there's a remainder of 12, or anything other than 0, this is not a factor. I need this to be a remainder of 0 in order for it to be, for x minus 1 to be a factor. So x minus 1 is not a factor. All right, so let's try another one. So sometimes when I chose a positive number, it seemed to build because I don't have a whole lot of negative coefficients, or coefficients here. So I'm going to try the other whole number, and I'm going to try a root of negative 3, which means that my factor is going to be x plus 3, right? So then we're going to do the same thing. These are the same coefficients of the polynomial, so I'm going to add down, and then I'm going to multiply through. Then I'm going to add down, and then I'm going to multiply through. I'm going to add down, and then I'm going to multiply through. I'm going to add down, and then I'm going to multiply through. Oops, note that's 0, Patterson. I'm going to add down, and then I'm going to multiply through, and then I'm going to add down. This remainder is 0. So that means that x plus 3 is one of my factors. Well, that's x plus 3 times, well, what's left? Remember, these are all, this is my constant, this is my x, this is my x squared, this is my x cubed, and this is my x to the 4th. This is how we build our polynomial after we found the remainder. So what I have then is 4x to the 4th minus 1. So we know that one of my roots is x is equal to 3. So again, when we set any polynomial equal to 0, now I can do this one. Now this one is nice and easy to factor. If you'll notice, it's the difference of two squares. So I've got x plus 3 over here. This can factor into the square root of the first and the square root of second. Remember, plus 1 minus 1. So again, setting each factor equal to 0. We already had this x plus 3 give us a root here. So if I set 2x squared minus 1 is equal to 0, I get x squared is equal to 1/2. Let me scroll up a little bit. So x is equal to the positive negative square root of 1/2. That's 1 over 2. Then if I have 2x squared plus 1 is equal to 0, then I have x squared is equal to negative 1/2. So x is equal to the positive negative square root of negative 1/2, which is not a real root. So if you look on your graph, if you happen to put this into Desmos or your graphing calculator, you'll find that I'll have a root at the negative square root of 1/2, positive square root of 1/2, and 3. So what we're going to be doing is we're using this idea of finding the possible roots, and then once we do, we get a remainder of 0, then we use it to find the next one. So let's go on to the next problem. So doing the same thing again, the factors of the constant term, the constant term is 2, so it's going to be positive negative 1, positive negative 2. The leading coefficient is 1, so the possibilities here are just positive negative 1. So what we're going to do is we're going to have all the combinations, positive negative 1, positive negative 2 over positive negative 1. So all of my possibilities are 1 over 1 and 2 over 1, looking at the number values, and then remember they're positive negative values of both. So now I'm saying, so I've kind of cued you into that direction. Use synthetic division to try 2. So we're going to do the root of 2. So remember that makes my binomial x minus 2. So let's go on and do that. So I've got coefficient of x cubed, coefficient of x squared, coefficient of x, and the constant at the end. So then we're going to bring it down, multiply through, bring it down, multiply it through, bring it down, multiply it through, bring it down. So there now I've got a remainder of 0. So that means that is a coefficient, that is a factor. And then the rest, remember we build it by the constant, our x squared. So the other factor is x squared plus 3x plus 1. And now I have to solve that. So the first root is at 2. Now this is where we have to find the other factor. So yes, x minus 2 is a factor. So 2 is a root. But we have to find the rest. So remember, finding the rest is putting all of these values, or putting that polynomial and solving that. And this is not one I can factor, so this has to go back to my good old quadratic formula, where a is equal to 1, b is equal to 3, and c is equal to 4. C is equal to 1, pardon me. And then we have to use the quadratic formula to solve. Remember, after this point, we set each factor equal to 0, and we solve it any way we can. Linears are easy. Quadratics require a different method of solving, either through factoring, quadratic equation, or factoring, completing the square. So put those values in and find the other roots. And solving using the quadratic equation, I get that x is equal to negative 3 plus or minus the square root of 5 all over 2. And those are the actual numeric value approximations, so you can look at them on the graph. So we have all 3 roots. So don't forget this, okay? So let's look at the next one. Finding the possibilities here. So all the factors of this constant term are positive negative 13. all the factors and positive negative 1, excuse me, I forgot that one. And then the factors of the leading coefficient are positive negative 1 as well. So again, we have all of our combinations of positive negative 1, positive negative 13 over positive negative 1. And typically, just because there are so many possible combinations that we're going to, your test questions will be something small like that. They won't be like 48 where there's so many factors. We're going to limit the combinations just so we don't run out of time. So the possibilities are, again, that we have 1 over 1 and 13 over 1, doing all the combinations of my top and bottom. And don't forget the positive negative. So again, the notes here kind of lead you into trying synthetic division with 1. So that means my root, or excuse me, my factor is x minus 1. So let's do a root of 1 with my lead coefficient on x to the 4th, x cubed, x squared, x, and the constant. So again, doing the synthetic, bring it down, multiply through. Bring it down, multiply through. Bring it down, it's positive 17. Multiply through. Bring it down, multiply through. And bring it down. So yes, 1 is the root, is a root, and then what we're going to do then is we're going to figure out what polynomial is remaining. And if you look, we're not yet to the quadratic, so I don't know how to factor this other than doing what we've done before. So if you look, from what I've created here, this does create this polynomial here. This is my remainder. The remainder of 0 says that it's definitely a root. And then I have the negative 13, the positive 7, the negative 5, and the 1. So then we're going to do the same thing again. The possible factors of the lead coefficient are positive negative 13, positive negative 1, just like what we did before. Same thing here, positive negative 1 on the coefficient there. So all the factors of 13 doing the same thing. Positive negative 13, positive negative 1, and then positive negative 1. Oops. Positive negative 1 is equal to all of my possible combinations, 1 over 1 and 13 over 1, again, positive negative. And this one is, again, guiding you through. So basically what we're doing is we're testing out the possibilities, and then we're going back and seeing what remains. Now, up until this point, you've been left with simply one, with a quadratic, which you can solve through quadratic formula. If you're not left with a quadratic like we are now, you have to simply do this process twice, whittle it down until it's something that we know how to solve. So using the synthetic division, let's put these values in. Again, the coefficient of 1 of x cubed is 1, then the coefficient of 5x squared, then the coefficient of the x, and then the constant at the end. So doing it again, bringing it down, multiplying it through, bringing it down, multiplying it through. That's a negative. Bringing it down and multiplying it through. And then I have a remainder of 0. So the remainder of 0, so that means x minus 1 is a root again, or a factor again. So when I've whittled it down, I've got an x minus 1 from up here. I've got an x minus 1 from down here. So I have 2 factors of x minus 1, or that multiplicity is 2. So we're going to bundle everything else up, but this is still x minus 1. So up to this point now, my f of x, which was originally, let's go back and look, it was x to the 4th minus 6x cubed. X to the 4th minus 6x cubed. Pause and get the rest of it. So this is the original polynomial. We factored out an x minus 1 the page above. We just factored out another x minus 1, so the root is still 1. Again, we can say that has a multiplicity of 2. And then this other factor is x squared minus 4x plus 13. So we found the root at 1 here, we found the root at 1 here, but now I am to a quadratic, so I have to find the rest. So a is equal to 1, b is equal to negative 4, and c is equal to 13. So pause the video and find that set of roots. So the final 2 roots are going to be imaginary roots. So if you look at your graph, if you happen to put that entire original polynomial into Desmos, you'll find that it only crosses the graph at 1. But with a multiplicity of 2, it actually touches at 1. And then the other two roots are imaginary. So there's only going to be one actual real x-intercept. So the last thing we want to look at is Descartes' rule of signs. So let me go pull that from the e-text. So Descartes' rule of sign is listed here on page 405 in the text. And basically, the values or the possible positive, negative zeros is depending on the number of sign changes in the original polynomial, or when we substitute in negative x. So let me show you an example. So here's an example of a function, and what we're looking at is how many times the signs change in the polynomial. So I went from a negative to a positive, so that's one sign change. I went from a positive to a negative, that's another sign change. And then I went from a negative to a positive, that's another sign change. So I have 3 sign changes, so that means there's 3 possible roots, possible positive roots. Descartes also said that we can continue to subtract even numbers. So if I subtract an even number of 2, I also have 1 possible positive root. So if I was looking at a polynomial that had, 7 sign changes, then I could have 7 roots. Subtracting an even number, I could have 5 roots. Subtracting an even number, I could have 3 roots or 1 root. So first of all, Descartes says when we're looking at all these possibilities, remember all the possibilities we made here, that in this particular one, I could have 3 possible positive roots or 1 possible positive root. Well, then we're going to look for what is the possibility if for a negative root. Well, for a negative root, we're going to put negative x into our equation. So this is negative 4, and then we're going to put negative x into each one. And work it out. And we get to this polynomial. So putting a negative x into the polynomial, the possible negative roots, real roots, are equivalent to the number of sign changes. Well, if I'm looking at this, if I've put negative x into the polynomial, I don't have any sign changes. It's positive, 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 positive. So there's 0 possible negative roots. And where this comes in really handy is when we're trying all these combinations. I again led you into trying 1, but noticing back here my possibilities were 1 or negative 1. But doing Descartes' rule of signs says, hey, I don't even have to try any negative roots, because when I've substituted a negative value in, I didn't have any sign changes. 0 sign changes. Substituting the negative x in means I have 0 possible negative roots. So that's what makes Descartes' rule of signs really handy when it comes to trying all these combinations.